Let's go for it. So 2.5, I think we're doing right. 2.5, 2.6 today? Okay, cool. So properties of functions. And last time we took a look at functions in terms of its definition, in terms of its notation, and now we're going to really take a look at functions in terms of its sort of more graphing than anything. A lot more graphing involved here. And we're going to look at something called relative maximum, relative minimums, and then something called even and odd functions, again, and something called the average rate of change, something you guys will see later on in calculus, almost the way you'll see it in calculus, but not quite. All right, so when does a function look like it's increasing? When is it decreasing? And when is it actually a constant function? Let's take a look at those first. All right, before we do that, let's talk about almost like defining a function here first. Defining a function says that if f is a function, if you let x sub 1 and x sub 2 be any two numbers on the open plane. So just to kind of draw it here. So you have x sub 1 here, and you have x sub 2. Good there? So they're any two numbers anywhere here. And they're on an open interval, which means the interval could start all the way over here, or the interval can go all the way over here. So somewhere where you have lots of space to work with, in a sense. Okay. Now the symbols a and b represent real numbers, and then you have negative infinity or positive infinity. So a could be representing negative infinity. B could be representing positive infinity. Just depends on what we're talking about. So again, if I say f of negative 1, that really means, let's say this dot is over here, that really is talking about that dot right there, right? The y value in that dot. So this is x sub 1. This is f of x sub 1. We're good? And then if I go all the way up here, actually no, I'm going to go down here. If I put this dot here, then this part right here would be f of x sub 2. We're good? So it's the y value, or the value at x sub 2. We're good? Just to understand that, let's go for it. So how do we define that a function is increasing? Mathematically, we say this. If x sub 1 is less than x sub 2, so x sub 1 is the smaller of the x values, then f of x sub 1 is less than f of x sub 2, and then the diagram is right here. Notice the a value is the open interval from a to b, and notice that f of x sub 1 is lower than f of x sub 2. And so we say that's increasing. Whenever you look at the x value to the right of the previous value, it's going to be higher, which kind of makes sense, right? Again, the way you'll see it in calculus is like this. All right, does that make sense in terms of notation right there? Okay, that's increasing, the calculus way of defining it. Then we have decreasing. See if this makes sense as well. So if x sub 1 is less than x sub 2, by definition, decreasing would be the fact that x sub 1 is going to be now higher than f of x sub 2. Okay, we're good there. So any x value that is to the right of the other x value is going to be lower. Cool, and the constant function. Here it is. Pick any 2 points, x1 or x2, on this interval, and you will have the same exact value, or the y value, or the functional value on that interval. Cool. What I want to emphasize this is, whenever you're talking about increasing, decreasing, or constant, it is always on an open interval. It is always, you go from here to here. You never do it on a closed interval. Are we good there? Because you never sort of say this is the cutoff. You're saying inside this interval it's going up. Inside this interval it's going down. Okay, let's take a look at the example first. All right, so when is this interval, when is this graph increasing? Well, it's increasing from here to here, is that right? Up to here. What we really are talking about is we're talking about the interval when it's increasing. So notice the little arrow that was right here? That means it was going further and further down, right? Whenever we talk about increasing, decreasing, always go from left to right. And so in this case, what we have is we have all the way from negative infinity all the way up to -2. This whole interval, this graph is increasing. Are we good? And then from -2 all the way to +3 on this interval, let me use a different marker here. On this interval, it is constant, not changing, and then it's decreasing from the open interval from 3 and again off to infinity, which is going to look more like this. Right? So it's always the x values. That's what you're looking at, and not the y values at all. And you're actually saying when is it doing it, as opposed to what are the values. All right, so here's your graph, all yours. Can you tell me when is this increasing, decreasing, or constant? All right, I'll do the increasing here, at least I can get here. So you would say this here, increasing, or A. Increasing would be anything that is higher than 2. Good there? There's my interval. My interval of increase is anything that is beyond 2. So from 2 all the way to positive infinity. Okay, next, when is this decreasing? It is decreasing negative infinity to 3. Right along here, it's going down, down, down until it hits to -3. At that point, changes direction. And so C would be, when is it constant? It's constant from -3 to +2. Notice it is always doing it on an open interval. We're not saying what's actually happening at -3. Okay. Let's do a couple more problems here, because I don't think the practice problem really did justice to this. So I have this one here. Can you tell me, I don't know, what should we call it here? Should we call it practice problem 1.3? Let's do that here. So this is practice problem. Haven't got to 2 yet, so I'm going to label it as 1.3. In between 2 and 3. All right, same thing here. Can you give me where it's increasing, decreasing, and then constant? And of course, there's one little weird thing here. Right at x equals 4, right, there's a corner there. Well, I'll give you a little hint, is does it change direction? That's my little hint. All right, let me start it as well here. So increasing, tell me if you guys agree here, it is starting at 3 and off to infinity. And again, ask me the questions if you need to. So right at 4, yes, there's a corner, but notice it's still increasing after 4. So because there's no change of direction, we include the corner as part of the increasing portion. Okay, any questions on that one? That was the weird one. All right, B. Where is it decreasing? Decreasing from -infinity to -2. Are we good there? All right, and then when is it constant? And it is constant from -2 to +3. All right, any questions on that? Problem. That should all work out. Okay, and one more.
If you get that increase, increasing 3
to infinity?
You get that 3 and then the positive infinity. How do you get that?
No problem. At 3 here, notice it is going to start to increase, right? It's increasing. At 4, there's a corner, but it's a higher increase. So really, if you're still talking about that, at 3.999, it's increasing, right? And then at 4.1, it's still increasing. So there was sort of no change in increasing or decreasing or constant. Even though it had a corner, it didn't change direction. So because it didn't change direction, we started off at 3, and it is increasing all this time, in fact forever, because of this little arrow. Does that make sense?
Yeah.
So you include corners as still increasing or decreasing as long as it doesn't change direction on you.
Okay.
Good question. Next one, let's see, let's call this a different name here. So that was 1.3. How about we'll call this practice problem 1.7. And then again, tell me where it's increasing, tell me where it's decreasing, tell me when it is constant. All right, how about this here? So increasing from negative infinity to positive infinity. Is that right? It is always increasing. There's never a time this thing turns or changes direction. Sometimes it flattens out a little bit more, but it never changes direction. So x cubed is always increasing. What we say here, you'll see it in calculus, is something called strictly increasing. So there's never a time where it goes a constant and then keeps on going. All right, decreasing, never. So in this case, there is no interval where this is decreasing. And when is it constant? Never. So in this case, it's going to be none as well. All right, so there's increasing, decreasing, and constant. Next thing to deal with is this whole concept of what's a relative max or a relative min. And pretty easy to understand. And again, but I really want you guys to understand the calculus notation for it in a sense. What you're saying is this. In a relative minimum situation, it is what we call the valley. It is sort of the bottom. Relative minimum is the very bottom of a corner. No, I'm sorry, not a corner, but a turn. And so we say this. We say that f of a is a relative minimum if you have a certain open interval again, in which any other f of x, given any x value, it's always going to be higher than that one for a certain time. So if I pick maybe like one over here, there's a f of x here, that red dot is still lower. Pick one over here on this side, still lower, still lower. So that f of a is the lowest point there. Cool. All right, relative maximum. Again, same thing here. Relative maximum just means it's the highest point. So I can pick a point here, still not the highest. Here, still not the highest. Still not. Yep. That red dot is going to be the highest point given any other x around it is going to be lower than that a point. Okay, another thing we should learn here. The textbook doesn't talk about it. I wish it did here. Whenever you talk about relative max, another word you'll see for it is called local max or local maximum. Again, relative minimum, you'll see it as local minimum. Good there? Relative or local means the same thing in calculus, just depending what textbook you use. All right, next. So when do you find relative maximums, relative minimums? You find them either on hills, which become relative maximums, and we call these valleys. Whenever you see a valley, those we call relative minimums. And then now we got some more vocabulary here. If I want to include relative max and relative mins, what do I say? And on this one, what we do is we just say extreme value, or you can say extrema. So if you say find all the extrema on this graph. Cool. Now you're looking for relative mins and you're looking for relative max. Okay, good there? Next thing, now let's go into something called turning points. So we talked about the hill and the valley, but really if you think about it, these extrema, the maximum, isn't it found when you are increasing? And then what happens is you start decreasing. Is that really what happens? So relative extrema are found when it changes from increasing to decreasing. Relative min, they're always found when you go from decreasing and you start increasing. Cool. So there's your connection between relative min and the increasing, decreasing, and constant functions. All right, let's jump to this and see how we can do it on a calculator. So I don't know if you guys brought your graphing calculators with you. If you didn't, if you can sort of look on with someone next to you here just for a little bit. All right. So these are the tests from symmetry from the other day's class here. I actually just copied and pasted them onto this right here. But this is symmetry with respect to the y-axis, or y-axis symmetry. But my question now is this guy a function? Does it pass the vertical line test? Someone said, yes, I agree. In fact, we have a function called x squared, right? This passes the vertical line test. It has y-axis symmetry. That's cool. So let's say it this way here. Functions can have y-axis symmetry. We're good? Next one. Does this pass a vertical line test? Ooh, okay, hold on then. So then anything that's symmetric with respect to the x-axis, not a function. We're good? Can we declare that right now? Because if you have symmetry, that means you have the same x value going to a positive y and a negative y. So this guy, not a function. With functions, you can't have x-axis symmetry. All right, how about symmetry about the origin? Does this guy pass a vertical line test? Sure does, huh? Okay, so in this case, if you have symmetry about the origin, you can still have a function. So the basic function that we usually look at is f of x is equal to x cubed. X cubed has symmetry about the origin, and it itself also is a function. So let's do this here. Let's go back to this whole y-axis symmetry. For something that has symmetry about the y-axis, we have a little special name for it. We call it an even function. And in terms of function, remember how we plugged in a positive x positive y, then we plugged in a negative x positive y and saw if we had those symmetries? In terms of function, you're going to really do the same thing, but you're going to do this. You're going to plug in a negative x into your function. And if you still get the same exact function out, you're going to say, yes, I have y-axis symmetry. I have an even function on my hands. Good there? Because remember, with symmetry about the y-axis, it was the x that changed. Okay, keep that in mind. And let's go to practice problem number 4. So let's show that squaring the squaring function is an even function. So if you take x and you square it, what we want to prove is we want to prove this here. That if you take a negative x into this function, you're still going to get the exact same function out. There's going to be no change. So tell me if you guys agree with this here. I'm going to plug in a negative x into my function. So what is negative x times negative x? Positive x squared. You still have the little negative on the outside just sort of hanging around, right? So we get this. And the question, I can drop the parentheses now, right? Because there's nothing to multiply in. And real quick here, isn't that the exact same function that we had before? So really what we just proved is we get the exact same function back. So we have just proved that plugging a negative doesn't matter with plugging in a positive. It returns back to the original function. Due to lack of time, let's not actually start graphing this, but I want you guys to see that little middle section. We plugged in a negative x. It would be the same thing as having a positive x, or you get the original function back. Okay, the odd function. That was the even function. I'm going to skip through this real quick. All right, we had the even function. Now let's talk about the odd function. Remember, the odd function is symmetry about the origin, right? So if you think about it, a positive x positive y gets me a negative x negative y, right? But now in terms of a function, if I have an x and a positive x, right? This is kind of like y here. That means if I plug in a, oh, not that one. If I plug in a negative x, what needs to happen is going to give me the opposite of my original function. Okay, we're good there? So here it is, plugging in a negative gets me an opposite of my original function. Therefore, I have symmetry about the origin. Technically, it's a y-intercept, sorry, y-axis symmetry, and then flipped. All right, let's see an example here, and then we'll go on from there. All right, so can we prove that negative x cubed is an odd function? Let's go for it here. We're going to plug in a negative into the function itself, or a negative x, and a whole bunch of negatives here is going to turn out here. So let's see what's going to happen here. This is going to be a negative x cubed, and when you cube something, when you cube a negative, it's still going to remain negative, right? So this is the way we'll show it. As you're cubing a negative times a negative times a negative, still is going to say negative. Now x cubed is just, that 3 is just cubing the x only. Again, now we're going to have to multiply. Negative times a negative is a positive. Again, a little bit of notation here. That's the simplified version, right? But now how do we prove that it's the opposite of my original function? It actually was already on the slide here. You'd have to say this. It's negative of negative x cubed. And that really is negative of my f of x. Okay, good there. So yeah, you didn't really have to bring it down all the way to x cubed by itself. You could have taken it right from here and went directly to this right here because it was an opposite of my original function. So there's the proof. Okay, there's the proof. But now let's go on to determining whether certain ones are even, odd, or neither. All right, so instead of just showing or proving something is an even or something is an odd, can you determine whether A, B, or C All right, so do you remember when we did this before? We had to test for each one of those, right? Didn't we? We said, okay, we're going to plug in a negative x, and the next time we say, well, we're going to plug in a negative y, then we're going to plug in a negative x and a negative y. For these, the cool thing about functions, you're just going to plug in a negative x and see what happens. Because based upon what happens, you're going to get yourself an even, odd, or neither. So let's go for it here. So for A, let's plug in a negative x and see what happens to this function here. So a negative x goes in, we're going to take that to the 4th power, and a negative x goes in and we're going to square it. In this case, negative x to the 4th power is just going to give us a positive. X to the 4th power minus 5, and again a negative x to the 2nd is just going to give us a positive. X squared, and that sure looks to me like the original function, doesn't it? And you can kind of see what's happening here. If you have, of course, even powers of numbers, obviously they're going to get rid of that negative. So in this case, how do we prove it? We say, look, we just got back to the original function again. So A, we declare to be an even function. For B, we're going to plug in a negative x. And if you want to, go ahead of me, go for it. If you can. All right, plugging in a negative into here. and plug in negative into here. Again, taking something to the 5th power leaves the negative there, so it'd be a negative 4x to the 5th. Taking something to the 3rd power obviously leaves the negative there, so we're going to put the negative out in front. Bless you. In this case, again, we're trying to figure out how we can get back to the original problem. We can only get back to the original problem by factoring out a negative, right? So how about if we take out the negative, we'll come up with 4x to the 5th plus 2x cubed, and isn't that the original function itself? Absolutely. So then in this case, what we've just proven, we've proven negative f of x. In that case, what do we say? I think I have an odd problem on my hands, is that right? Or an odd function. Okay, C, h of x is 2x plus 1. Prove it if it is an even, odd, or neither. All right, let's go for it. Again, negative x into the function itself gives me a 2 times negative x plus 1. That will give me a negative 2x plus 1. All right, and what do you guys say? Well, it's not the original function, right? If I were to factor out a negative out of here, which kind of would help maybe, I do get the positive 2x, but now I have myself in minus 1, and that's not my original function. So can't have the original function. I factor out the negative. I still don't have the original function. In this case, then we say it is neither. We're not going to have any kind of symmetry here at all. All right, second to last thing to do, something called the average rate of change of a function. And I kind of put in a few other things into here, just so for you guys to recognize it from algebra here. They have it in terms of functions here. They say a and f of a, then they say b and f of b in your textbook. And what they say, well, that means it's f of b subtract f of a, b minus a. But where is all this coming from? So I'm going to go back and sort of redo it in terms of algebra. If I say a is really x sub 1, and f of a is really y sub 1, and b is x sub 2, f of b is y sub 2, this is just going to be the slope formula. That's all it is. It's a slope formula from algebra, but now in terms of a function. Okay, good there? So you got yourself the slope formula just in terms of a function itself. And that is called the average rate of change. So let me at least kind of explore this idea just a little bit further here. Because remember in algebra, in slope doesn't give you exact change of things. It gives you a change over time. So this little example here, this was, I just kind of got a, let's see, a concentration of blood of a, like a prescription painkiller. And so if you take it by form, what's going to happen is you take it, and then what happens in about 2 hours, you get the maximum amount of concentration, and then from here, then it sort of slowly goes down. That's whenever you go to the dentist, you get your wisdom teeth pulled, like I've had before. They say take this every 2 hours. Why every 2 hours? Because of that sort of concentration. For a capsule to sort of go into your bloodstream, it takes about 2 hours. But so if I were to take the average rate from here to here, that would be pretty good, significant, right? Because it tells me on average this is how fast the concentration is happening in your bloodstream. We good? What does not make sense if I were to do this, if I were to take the slope from here to here. Does that make sense? Because what's the slope right there? It's 0, right? So we kind of always have to think about, is this appropriate to take the average rate right now? So whenever things are sort of almost linear, that's when we take the average rate of change. Right here, we would not do that because from hour 1 to hour 12 almost, technically the slope is saying nothing changed. But there's a whole bunch of stuff that changed. We good? So always think about when it's appropriate to take the average rate of change or not. So practice problem number 7. Can you find the average rate of change of f of x, 1 minus x squared, as it goes from 2 to 4? All right, how do we do this here? It would be easiest to plug in the value itself. So first saying it goes from 2 to 4, let me plug in, see what it is at 2. According to my function, I'm trying to find is 1 minus 2 being squared. In this case, it would be 1 minus 4, or how about a negative 3? So I'm kind of just doing individual points. I'm actually taking this back to algebra. I'm saying what's my x coordinate, what's my y coordinate. All right, so f of 4 now, because that's the end result, I'm going to say 1 minus 4 being squared, which makes 1 minus 16, which makes a negative 15. So really I have 2 points here. One point is 2, negative 3, and the other point is 4, negative 15. All right, so the difference between A and B, A is going to be the smaller of the values, B would be the bigger one here. So if I go back to f of B minus f of A over B minus A, for me the 4 is going to be the B and the 2 is going to be the A. So how about this here? Let's go with negative 15, subtract a negative 3. On the bottom it's going to be a 4 minus 2. And so how about a negative 15 plus 3 over 2, or a negative 12 over 2, or a negative 6, eventually at the end of it all. So again, that's the average rate of change. All right. So this one, in this case, we evaluated at the first point, we evaluated at the second point, and we come up with a slope between those two evaluated points. Sometimes what we do like to do is leave one of them as variables anyways. So we have this little thing where we still want to see, we want to make a function that gives us the slope at a certain point from a certain distance. So the example, and I don't know if this is in your textbook here, tell me if this is right or wrong here. Do you have an f of x, or do you have an f of t? Cool, good, good. That's the way it should be here. This should be f of t, because you're saying the variable is t, and there it is, 2t squared minus 3. Okay, so what we want to do is we want to see the change from t is equal to 5 all the way to t equals x. So notice this time, x is the endpoint that we want to finish off with. It's kind of cool. So now we're plugging in the variable. We're allowing things to change. So by example here, here's my function. Here's my b value, subtract my a value. Again, here's my f of b, subtract f of a. And if we do that, notice the x stays, or the x comes in as the variable. For the end result over here, the a value comes in as 5. At this point, yes, you do have to square this. You do have to do the work for it, simplifying out and factoring out a 2, and then factoring some more leaves us with a function now, as opposed to just a certain point. So what does this give us? This gives us the average rate of change from 5 forever of this function. So let's see, if I were to graph it like this, it would be something maybe like this. So 1, 2, 3. It goes like this. It goes x squared minus 3. And so let's say right at 5, it's kind of fast graph here. So let's say x equals 5 is about right here. And so it's saying that if I go to 6, I can plug in a 6 in here, and it'll give me the slope from 5 to 6. If I plug in a 7, it'll give me a slope from 5 to 7 right away. So I've made it one point to be an endpoint, and the other to be a variable point all the way out to however long I want it to be. All right, for you guys, practice problem number 8. All right, can you do the same thing that we did on the example problem number 8? So the function is f of t is 1 minus t. I'm going to start at 2, and we're going to go all the way out to x. We started off here, so f of b minus f of a, technically there's the formula, b minus a. So if I were to plug in b into my equation, or x into my equation, it would be 1 minus x. That's f of x minus f of 2 over x minus 2. All right, simplifying as much as we can here out. You can drop the first parenthesis, that's pretty easy. 1 minus 2 is a negative 1. Still x minus 2 on the bottom. And subtracting a negative 1 is really adding positive 1, so 2 minus x, x minus 2. There's a little thing from algebra here. Hope you guys know what to do here. Kind of see that they're both opposites of each other. And because of that here, you can either switch them around on top, x minus 2 on top, you got to put a little negative out in front, cancel off the two terms, or you could have canceled right away, just leave a little negative 1 on top. Alright, so for this one, this is funny. If you start off at 2 and you go any length out, no whatsoever, the slope will still always be negative 1. It does not change. Okay, and again, just real quick here, what does this say? X minus t, technically what it is, it's a graph that goes like this. There's my original graph, this is f of t. my x coordinate is 2. And it says if I go any length out, if I go out all the way to 3, my slope will still be a -1. If I go all the way out to 4, my slope is still -1. If I go out all the way to 20, my slope will still be -1. We're good? That's kind of what you're looking at. Okay, and let's go to this here. So far we've been starting with an a value going up to b value. Then we started going with from an a value to a variable, right? Just the function itself. So now let's do this here. Let's see if we can make it from any x whatsoever, and we go out as much as we like out. So we're going to sort of like put 2 variables into this situation. Okay, so there's no starting point anymore. So let's see if we can create this. So first and foremost, what I'm going to do, I'm going to explain the concept here, and then we'll do the notation here. Let's say we have a parabola here. Let's say this guy is x. Cool. Here's what I'm going to do. I'm going to have to somehow put 2 variables into here. And the way I do it, I do like this. I say x is my starting point. Cool. And what I do is I'm going to go out from x a certain amount. I'm going to call it h. Now h could be 3. H could be 1. H could be 0.1 or 0.00001. H could be as big as you like or as small as you like. Good? So just for an example here, what happens if x is 3 and h is 1? What's this point over here? Everybody okay with 4, right? You just went to the next one over. So how about if x is 3 and h is 0.01? What's this point here now? Yeah, 3.01. We went 1/100th of a space away from 3. We good? Okay, so there's the concept. So now let's take a look at the notation here. So back all the way to algebra. Let's see if we can put all this together. y2 minus y1. x2 minus x1, are we good there? Then what we do is we bring it into this interesting notation in terms of function, right? So f of b minus f of a. We looked at that before already, right? So here's what we're going to do now. We're going to say that this b value is whatever x is plus h. Good there? The a value is just going to be x itself. Good there? So let's see what happens here. So now on top, this is going to be f of whatever our starting point is plus little h. Subtract what our original starting point was in the first place. For the b, looks like we have x plus h minus x, right? Can we simplify that just a little bit more? Not the top. Can't simplify the top at all. But the bottom? And doesn't the h's go away? I'm sorry, the x's go away? You can drop the parentheses completely. And then you got yourself these 2 x's are gone. So final formula, f of x plus h minus f of x over h. How's this awesome? This is almost the formula for derivative in calculus. What you've done is you've eliminated all possible numbers in here. You can pick any starting point you like, and you can pick any distance you like. But you've created, in a sense, a formula with 2 variables inside it without having to start somewhere or anywhere. Okay. This is called the difference quotient. The difference quotient, we need to add one little extra thing in here and it becomes a derivative. Okay, let's see how are we doing on time. Let's try it. All right, looking at the example before we begin. It's 2x squared minus 3x plus 5. Here's my f of x. What we want to do is we want to calculate the difference quotient here. And again, you guys will have a whole bunch of fun on the homework with this here. So we have to plug in 2x squared minus 3x plus 5 into this function right here. So how do we do that? It's probably easiest to calculate what is f of x plus h first. I think we've been doing that already, is that right? I think we calculate f of x plus h. So plug it in. Again, it is going to always be this right here because it's just a expansion of x plus h. Multiplying the 2 in, distributing the negative 3, and eventually you have this right here as now f of x plus h. So now we start substituting into our difference quotient. It looks pretty big just because you have a trinomial in your hands, but here it is. This is f of x plus h. This is the original f of x. Get rid of the parentheses, and then we start taking off any terms that are the same. In this case, there's that, and there's this one. In fact, everything inside the f of x should cancel. You also should have, every single term should have an h in it. If you don't have an h in every single term, that means you did something wrong. Factoring out the h cancels, and there it is. There is a formula that will calculate slope given any x and given any h whatsoever. Your turn. Let's go for it here. Practice problem number 9. Can you calculate the difference quotient of negative x squared plus x minus 3? Give you guys a couple of minutes here. Try it yourself. Then after you do that, maybe look at the neighbor next to you to see if you guys at least got the same thing. It could be that both of you guys are still wrong, but maybe that's not the case. All right, let me give you at least a part of the answer and kind of look up if you're at least that way. So let me calculate f of x plus h for you. Let's see if we at least have that correct before we start plugging everything in here. So negative x plus h squared, that'll be x plus h minus 3. So factoring or expanding out x plus h would give it x squared plus 2xh plus h squared. Again, you can FOIL that out if you like. You're still going to get the same thing here. All right, dropping all the parentheses, which means multiplying through that little negative in the beginning. In this case, that's what you should be plugging in for f of x plus h. Let me give you at least that answer for now, and then see if you guys can plug it in. All right, let me go with plugging in the values here. So here's f of x plus h. From the previous slide, here's subtracting off the original function itself over h. And my little shortcut here is that you don't really have to get rid of the parentheses, because what happens here is you can really cancel everything that's the same in both parentheses because you got subtraction in your hands. So if you have a negative x squared in one and you have a negative x squared in the other, you should be able to cancel those because you're subtracting those out. And a positive x in one, positive x in the other, those go away, and a negative 3 in both. Notice that everything in the f of x has to go away. Sometimes you do have to simplify, especially when you have fractions here. You want to get common denominators. You're going to do a little bit of work that way to get things where you need to be. How about a negative 2xh minus h squared plus h? Again, doesn't have to really be in order, but you should have h's everywhere. In every single term, factoring out the h leaves us with a negative 2x minus h plus 1 looks like. Still divided by h, but if you can factor out the h, you can also cancel the h out. When you do that, you get yourself a negative 2x minus h plus 1.